Okay, so this is page 211, kinetics and equilibrium. So some of the stuff on this note page is pure review, and then there are some new ideas. So take a look. Two terms that we have learned since the beginning and put in practice since the beginning of the school year: exothermic and endothermic. So in an exothermic process, the reactants need to release heat into the surroundings in order to form those products. And as a result, the surroundings warm up. Okay? Versus an endothermic process, the reactants need to absorb heat from the surroundings, so they take it from the surroundings in order to form the products. And as a result, the surroundings tend to cool down. Now, sometimes we get a little confused, like, what is the surroundings? So examples of the surroundings in chemistry class. Number one, a lot of times, the air in the room. Does the air temperature go up or go down based on a process C? Many of our lab experiments occur in water, and water is not a reactant or a product, but it's a medium to help the process take place. So does the water's temperature go up or down? Is the water warming up or cooling down? And then also the container in which is holding the reaction, like that beaker, test tube, flask. So examples of the surroundings. So we have been using these definitions for a while. We're going to throw in another new word, or it's newer for us, is enthalpy, which is represented by a capital H, and it represents the heat content of a substance, and it's specifically based on 1 mole of that particular substance. So how many joules or kilojoules of energy are present in 1 mole of that substance? So now we have to take these ideas of exothermic and endothermic and finish up these ideas of these potential energy diagrams in which we started working with earlier in the year. So to do that, I need to introduce a couple more terms. So here's this term, activation energy. It represents the amount of energy that is supplied to the reactants to kickstart a reaction. And if you were in class, you saw me play with a match. So a great example of activation energy would be striking a match to light. Once when you have struck that match and it lights up, the combustion process continues without you continuously striking the match. So the activation energy, I like to say, it's like a one-time deal. It gets it going and then it's done. And you might see me short form activation energy as AE. Another term sounds kind of similar, activated complex, so I'm going to probably short form that as AC. It's not a true reactant or product, but it's an intermediate substance between the reactant and product. If we supply the right or correct amount of activation energy, that means that the reactants form the products. So the reaction actually, or the process of change, occurs. If we don't supply enough activation energy, maybe we get the reactants moving around and doing some collisions, but not enough for the full reaction to occur, then those reactants will fall back and remain as reactants. Okay? So now let's take a look at these diagrams. So earlier in the school year, I introduced potential energy diagrams, and I said that these are the diagrams. They have the two platforms and a hill that connects them. The platform, most to the left, always represents reactants, and the platform to the right always represents the products. The y-axis is labeled as the potential energy, and remember, potential means stored energy. So if we took the reactants platform and we had scaling in red off the y-axis, we would know how many joules or kilojoules of energy is stored in that substance. So if that's true, arrow 1's position, where it starts at the x-axis and it reaches to the reactants platform, we should label this as the potential energy of the reactants. Now notice arrow 5 is kind of similar to arrow 1. It starts at the x-axis and it ends at a platform, but it's a different platform, so we should label this as potential energy of the products. Now we have a bunch of other arrows. Now take a look. Arrow 3 is different than arrow 1 and 5 because it doesn't start at the x-axis, but it actually starts at the reactants platform and it reaches the peak. So the reactants have a certain amount of potential energy, but arrow 3 represents that extra supplied energy to the reactants. So arrow 3, since this is supplied energy to the reactants, we would say it represents the activation energy, the kickstart. Now notice, arrow 6 is kind of similar to arrow 3. It doesn't start at the x-axis, but it starts at a platform and it ends at the peak, like arrow 3. Starts at a platform, ends at the peak. Starts at a different platform, but it ends at the same peak. So because it's similar to arrow 3, arrow 6 must represent an activation energy. So here's the difference between these two activation energies. In science, you know that when you have a diagram or a graph, you need to be able to look at it in the normal direction, left to right. That means you're looking at the forward reaction. But once in a while, you have to look at it from the opposite, where you're going from the products back to the reactants. So that would be the reverse reaction. So if we were trying to make these reactants go up this big hill to reform the reactants, this is the amount of kickstart or energy we would need. So arrow 6 is the activation energy of the reverse reaction. If you're asked for plain old activation energy, it's normal forward direction. If you're supposed to talk about it for products back to reactants, then you will always see this word reverse there. So only worry about products back to reactants if you see the term reverse. Now, arrow 2, okay, it starts at the x-axis like arrows 1 and 5, but it doesn't end at a platform, it ends at the peak. And notice that peak is kind of in the middle between the reactants and products. So the position of the peak represents that activated complex. So I'm going to put AC there. So if the tip of the peak represents the activated complex, and I need to read something off for arrow 2, I would label this as the PE of that activated complex. Now we have one more arrow, and this is a really important arrow. We see that it specifically goes between the reactants platform and the products platform. So the PE of the reactants compared to the PE of the products. So that means that we have our final PE compared to our initial PE. So that must be our delta H, the heat of reaction. So I'm going to maybe put that in parentheses. So the heat of reaction. And these delta H values, if we need to know it for a particular reaction, is on table I. So now I want to just point out one more thing, that we talked about this early in there. For the reactants to get to the activated complex, the reactants have to absorb energy. And then once when they reach that and they're heading down to the products, we see then a process of release. If I can write that there. So now when you compare how much energy the reactants have absorbed to the amount that they have released, we can see the release hillside is much longer. So in this case, the reactants release more energy than absorb. So they had to release. And if I was to write anything else down here, I would say that the reactant PE is greater than the product PE. So in this case, because overall the reactants had to release energy, they started off with more potential energy, that I would say that this diagram represents an exothermic process. Okay, quickly let's go through the bottom diagram. Notice it's kind of similar. We've got two platforms and a hill. So if we look at this, arrow 1, x-axis to the first platform that represents our reactants, so PE of the reactants. Okay, arrow 2 goes from the reactant platform to the peak of the hill, so I would say that that's an activation energy. Arrow 3 starts at the x-axis, ends at the peak of the hill, so I would just say that this is the PE of that activated complex, and I would put an X to show the location of that activated complex. Arrow 4 starts at the x-axis and ends at the products platform, so I would say this is the PE of the products. Arrow 5 starts at the products platform and it goes to the peak, so this is also an activation energy, but it's of the reverse reaction. And then arrow 6 is that region between the two platforms, so this must be a delta H value. Now, in this case, take a look. Reactants here, products here. And if you take a look at the hill, of course, the reactants leave their platform, you're going up the hill, so that means that they need to absorb energy, and then when they reach the peak of the hill and head towards the products going downhill, they are releasing. But in this case, the absorption side of the hill is much larger or longer than the release. So in this case, the reactants absorb more energy than release. And as a result, the reactant PE, oops, let me move that up, so the reactant PE, look at it, it's lower, it hits the y-axis in a lower position, right? So the reactant PE is less than the product PE. So overall, since the reactants had to absorb more energy than they released, this diagram overall, okay, so this diagram overall would represent an endothermic process. Be able to label any arrows on any PE diagram, identify if it's endo or exothermic, and be able to compare reactant and product potential energies.